Hello. Today we are going to start a new chapter about simultaneous equations model, usually called as the SEM. And its the references for this chapter are also on Root, Green, and like I say, almost any textbook has a SEM chapter, so you may use them. They may different a little bit, but the idea is of course the same. So it does not matter whatever you use. So let me start with start with the examples for the simultaneous equations model. Maybe the most famous and most common example, most widely used example is the supply and demand functions. Think about demand function given by quantity. Quantity is a function of price, and supply is another function for quantity as a function of price. And just to show you it's downward sloping and upward sloping, I used plus minus there. And then we observe Q and P, the equilibrium quantity and equilibrium price, which is determined by these two equations, two functions. In here, we would like to identify beta and delta. Usually, that's what we are interested in. So beta is a parameter that captures the elasticity of the demand function to price, and delta is the supply elasticity. So usually the elasticity is important when you calculate the like monopoly profit or the marginal revenue or the deadweight loss from tax. Uh, so we would like to identify this, but can we identify them? If not, what's the required assumptions? What's the assumptions we need to add to identify them? That is example number one. Example number two, Keynesian consumption model. So it's a very simplified model. It is like you can extend the macro model as much as you want. So let me give you the simplest possible example. The consumption is determined by income. So C is consumption, Y is income. So consumption is determined by this way. Beta is the marginal propensity to consume, and investment I is a function of interest rate R. So if the interest rate increases, investment goes down, and vice versa. And equilibrium is determined by the income equals. So the income is the total consumption plus investment plus government spending, right? So, or like if you allow open economy, you may want to add net export here, and also you may add more things like inflation, prices, but let's keep it as simple as this. And we would like to identify these parameters. Say, for example, beta, the marginal propensity to consume, is an important parameter to measure the effect of government spending. If you remember the multiplier effect, that depends on beta here. And delta is the sensitivity of the investment to interest rate. So it is of great interest how much interest would have effect on the investment. So if the Fed increases or decreases the interest rate by say 25 base points, then what would be its impact on the economy, for example? Anyhow, can we identify these parameters or not? That is a question. And third example is from game theory. So Chrono duopoly. Think about Chrono game. The demand function is given by this. If the first firm 1, produces Q1, firm 2 produces Q2, then the total supply is Q1 plus Q2, and in the market, the price is determined at this level, like determined by the total supply according to this demand function. It's actually an inverse demand function. So given the supply, price is determined. And then, based on the demand, firm 1 solves the profit maximization problem and obtains this function. This is the best response function, or the first order condition of the profit maximization problem. Then that is represented as a function of Q2. So given the opponent's choice, I am going to respond like this. So given Q2, this is my best response. And similarly, the firm 2 is symmetric. Given Q1, the firm 2 will react like this. And by solving these three equations, we observe Q1, Q2, and the price. Of course, C1, C2 are constant marginal costs. And then from this, can we identify beta or like some parameters like cost and yeah, that's the parameters that we would like to identify. And then in this model, so simply speaking, as you can see, the simultaneous equations model, it means a system of equations. Usually I'm like usually linear, but you may relax the linearity if you need. But here I will maintain linearity assumption. So anyhow, there are several equations, and the several equations at the same time generate multiple random variables at the same time. That is one possible way to understand this, like this. Say two equations, demand, supply, determine quantity and price. And three equations determine consumption, income, and investment. Like if you assume that interest rate and government spending is chosen by the government, not within this equations. And here, Coulomb-duopoly equilibrium is a solution to these three equations. Also, the solutions are P, Q1, Q2. Three equations determine three equilibrium. That is the basic idea of simultaneous equations model. We are like, so again, it is important to understand what is determined within the model and what's not. So as I explained, say in the supply demand, price and quantity are endogenous because they are determined by the model, by those two equations. And in Keynesian model, macro model, consumption, investment, and income are endogenous because the equations is to explain how they are determined. But I do not know how the interest rate is determined or the government spending is determined. So we usually assume that interest rate and government spending are exogenous. And also in Coulomb-duopoly model, equilibrium price, equilibrium outputs are endogenous, right? The model generates, the model is to explain how the equilibrium output is determined. But like say, for example, marginal cost is exogenous, but it is usually not observed. Anyhow, so like this, we are handling endogenous variables, multiple endogenous variables using multiple equations. So it is an extension of the linear regression model to multiple equations. And the equations. So let's put it this way. So the classical linear regression has only one equation. And when we study the instrumental variable linear regression model, we extended the classical linear regression model to a triangular equations model. If you remember, triangular equations model is like y is a function of x, and the endogenous variable x is a function of z. So that was a triangular equations model. In that case, there are two equations, an equation for y, an equation for x. So the first stage equation, second stage equation, and two endogenous variables, x and y. And in this case, so the IV linear regression two-stage regression model is an example of simultaneous equations model, the simplest possible example. because simply each equation determines one. There is an order. Z determines X, and then X determines Y. So it's simple, and there is no reverse causality. So Z affects X, X affects Y, but not the other way. So Y may affect X, but that is not allowed in the triangular equations model. But in general, in simultaneous equations model, they may determine each other. Like, say, think about this: QP, quantity and price. Even if I said quantity is determined by price like this, but it is not that only price affects Q, but Q also affects price. So they are simultaneously affecting each other. That is a more general model than the triangular equations model. So this is and then we can think about two different ways to understand the simultaneous equations model. First, you can think about the structural form, which shows the underlying relationship among the endogenous and exogenous variables. It is more related to closer to economic theory, like the examples. This example is like just game theory model and a micro model like macro model. So, and it explains like alpha, beta, gamma, delta has their own meaning. Like say, alpha is intercept for demand, gamma is intercept for supply, beta is elasticity, delta is elasticity, like that. So each parameter has meaning, economic meaning, and each equation has economic meaning, and combining them, the observations are determined. That is structural form. On the other hand, the reduced form is a more convenient expression of the equations. Like, so reduced form is a solution for the endogenous variables in terms of exogenous variables. So for example, go back to the supply and demand example. In demand and supply, both equations are a function of Q. So Q is this and Q is this, which is not convenient. So what you want here is Q equals to something and P equals to something. And you can rewrite that way. You can rewrite these equations into Q equals to something, P equals to something. That is possible. That is, if you rewrite that way, that is the reduced form. So reduced form is the solution, equilibrium, from this system of equations. So based on the reduced form equation, you can see that how the equilibrium is determined, but it does not show the relationship between like a Q and P in the demand or in the supply. So that's the difference. Later, you will see what's the difference. And here in this chapter, I am going to use Y for endogenous variables. All Y are that there will be multiple endogenous variables in a system of equations. So there may be multiple Y's, and also X is for exogenous variables. So whenever you see X in this chapter, assume that it is exogenous. And of course, exogenous variables are assumed to be uncorrelated with the error terms. So that's the basic assumption. And from now on, all random variables have mean zero. Y is mean zero, X is mean zero. So I will drop the intercept, and all the variables are interpreted as a demeaned variable. Okay, so then this was the introduction, and in the next video, I will start from the very simple 2x2 model, and then I will extend to more complicated cases and what we can do, to see what we can do and what we cannot. And it will be fun to see the pattern. Okay, see you in the next video. See you later.